All right, everyone. So I want to finish off and do the last question we had here in 4.5. It was a slant asymptote question. You have one of them in your homework, which is why I wanted to kind of go through it with you guys. And it's definitely a little bit slightly different than what we have been doing. So just as a reminder, a slant asymptote occurs when the degree of the numerator is 1 more than the degree of the denominator. And we find what the slant asymptote is by long division. Now, if you need a reminder on that, we're going to go through that here. So sketch the graph of y equals x cubed over x squared plus 1. All right, first things first, we talk about domain. All right, and then here, even though it's a rational function, right, we have a polynomial over a polynomial, this denominator never ever equals 0, right? X squared plus 1 is equal to 0. We would get x squared is equal to -1, which can't ever happen. We don't deal in complex numbers. So we actually have all real numbers as our domain, or from negative infinity to positive infinity. All right. Next up was we did x and y intercepts. All right. So we did this a bunch of times already. Our x-intercepts were when y is equal to 0. And when we set y equals to 0 in a rational function, I only care about where is the numerator equal to 0. We've talked about this a bunch, right? So x cubed, is equal to 0. We would get x is equal to 0. So there's my x-intercept 0, 0. And if this is your x-intercept, it will also end up being your y-intercept, right? Because that's also where an x is equal to 0. But we can prove that really quickly as well. So y-intercepts occur when x is equal to 0. Y is equal to 0 cubed over 0 squared plus 1, 0, right? So we have x and y-intercept just end up being 0, 0. Third thing we talked about is going to be symmetry. So we have f of negative x is equal to, and what we want to do is we want to plug in and see what we get. So what we're going to get is negative x cubed over negative x squared plus 1. Now when I cube a negative, I'm just going to get that thing back. So it's going to look like a negative x cubed over, and negative x squared plus 1 just becomes positive x squared, right? Squaring something becomes positive. This is the same thing as negative f of x. If I just shove a negative in front of this thing, you would just get negative x cubed over x squared plus 1. So because these two things are the same, this is odd and it's symmetric about the origin. Very exciting. And then for step 4 is our asymptotes, right? So we have no vertical asymptotes. We have no vertical asymptotes because there's nowhere where that denominator is equal to 0. So vertical asymptote, none. Now horizontal asymptotes, that's when we look at the limits as x goes to infinity or negative infinity. So I have x cubed over x squared plus 1. Now, we could use L'Hopital's rule here and determine kind of what happens and say, okay, like what happens when we take the derivative of both. And we can use L'Hopital's rule because I have infinity over infinity. So that works out. So let's do it. I'm going to show you kind of how this shakes out here. So L'Hopital's rule, LH, tells me to just take the derivative of the top, we get 3x squared. Over the bottom, the derivative of the bottom would just be 2x. All right, so the limit as x goes to infinity of 3x squared over 2x, and x cancels out on the top and the bottom. And I'm left with 3x over 2. Now, that's a line, right? 3x over 2 is a line, 3/2 x. As x goes to infinity, this thing will go to infinity. All right, this thing will just get bigger because it's a line, right? We know how the line works. And then for similar reasons, when x goes to negative infinity, all these two like intermediate steps are the same, right? So as x goes to negative infinity, this thing will become 3x over 2, right? X cubed to 3x squared with L'Hopital's rule, so same. And as x goes to negative infinity, this is a line, this thing will go to negative infinity. All right, so there is no horizontal asymptotes. The limits at infinity tell me that, all right, that none exist. So What we do have here, though, is we have what we call a slant asymptote, and we believe that we have one because the degree of the numerator is 1 degree more than the denominator. All right, and you may not have done this since like pre-calc, depending on like algebra 2, maybe you saw it in algebra 2, but definitely in a pre-calc class you would have seen this. So the slant asymptotes, what we do is we divide the bottom, the denominator, into the numerator. So what this looks like is it looks like x squared plus 1, okay, long division. Now, the top part is just x cubed, right? However, we need to make sure that we have all the other like x's so that we have placeholders when we do this long division. So even though it's not written, when I apply this long division, I want to make sure that I still have the x squared, the x, and like that constant piece. So even though they're not existing, we need them as placeholders when we do this long division. All right, so I know this has been a while. So what we do is we take the first term on the outside and divide it by the first term on the inside. So I'm going to divide x squared by x cubed. So x cubed over x squared. What you just get is x. All right, x. So the little mini math that's going on here is we're doing x cubed divided by x squared, and we're only dividing with those first terms. When I do that, you just get x, right? That's the only thing. We get x. I'm going to put that x over that x placeholder, and that's why we have it, so that when we do this long division, even if we don't have it in the original, we have a spot to put it when we do the math, right? Back when you learn long division in like elementary school, you learned like everything goes in like their little house or however they teach it nowadays, but that's the same idea. And then what we do is we subtract this top x times x squared plus 1. So we subtract, well, first we should multiply. Let's multiply first. We do x times x squared plus 1. We'd get x cubed plus x. And that's what we're going to subtract. And I'm going to put it in parentheses so I know to distribute the negative. Now, I don't have a x squared, so I'm actually just going to make this a 0x squared. I'm going to turn that second parenthesis into a 0x squared, but I have an x. All right, so x cubed plus x can be written as x cubed plus 0 x squared plus x. And when we distribute the negative, x cubes are going to cancel out, x cubed minus x cubed, 0x squared minus 0x squared, and 0x minus x. We get negative x. Now, I can't do any more division. I can't do negative x divided by x squared. So like this is what we call our remainder. What this is telling us, right? Like I know it's been a while. You may not have seen this for quite a bit of time. What this is telling us is we can actually rewrite this equation as x from x up here minus x, so minus x from here, over x squared plus 1. Like they mean the same thing, all right? We just typically don't write it like that. But we can say that that's an equivalent thing. So what this is saying, what we have done here is we've now shown that we have a slant asymptote, and our slant asymptote is that line that we found, that line y is equal to x. All right. So when we graph this, we're going to have an asymptote at this line, y is equal to x, and it looks kind of crazy, but it'll be all right. We'll take a look at it. Okay. Now let's get into the calculus, right? So step 5. So step 5 says x cubed over x squared plus 1. Step 5 is going to be your first derivative, increasing, decreasing, all that good stuff. So first things first, let's take a derivative. U is equal to x cubed, right? U is equal to x cubed. U prime is equal to 3x squared. V is equal to x squared plus 1. V prime is equal to 2x. So this is what we got. Let's set up our quotient rule, and we'll find our critical values or critical numbers. Y prime. V times U prime. So I'm going to do 3x squared times x squared plus 1 minus 2x times x cubed. So we go U prime times V, and then U times V prime, all over V squared. So I have 3x squared times x squared plus 1 minus 2x times x cubed over x squared plus 1. Now, I want to simplify the numerator because, once again, we're going to have to work with this, so let's simplify it down as much as we can. So what I'm going to get is 3x to the fourth, right, distribute, plus 3x squared minus 2x to the fourth, all over x squared plus 1 squared. So this actually simplifies down really nicely. We're just going to get x to the fourth plus 3x squared over x squared plus 1 squared. Now we have to set this thing equal to 0. So that means, or we have to find where this is not equal to 0 and where it doesn't exist. Now we know that this bottom never not exists, right? So we know that x squared plus 1 never equals 0. We've already talked about that up in step 1 with the domain. So the only thing I care about is x to the fourth plus 3x squared is equal to 0. And I'm going to factor out an x squared, be left with x squared plus 3 is equal to 0. Okay. Well, this is actually not too bad. X squared is equal to 0. So x squared is equal to 0, which means x is equal to 0. And x cubed plus 3, x squared plus 3 equals to 0 never happens. Right? Doesn't exist. We get x squared is equal to negative 3. We don't deal with complex numbers in this course. So 0 is my only critical number. So really the only thing that's different about this entire problem is this slant asymptote piece, and the only time that that's going to come up is when we graph it, right? So the only new thing with this problem is this piece. Everything else is the exact same, and this is the only thing that's going to matter. The only time this is going to matter is when we actually graph this thing. So all of this is really done the same way. We're going to have negative infinity to 0, 0 to infinity. That's our interval. We're going to pick some test values. Negative 1 and 1 sound good. If you like to label out your rows, that's cool with me. And then the sign of f of x, this thing, if I plug in negative 1, is always going to be positive, x to the fourth plus 3x squared. Whenever if I plug in negative 1 up here, this is going to be positive. This is going to be positive. And same thing if I plug in positive 1. You can check those numbers if you'd like, but it's always going to be positive. So what this tells me is that this thing is always increasing, all right? And it's always increasing from negative infinity to positive infinity. Something strange is going on at 0. Always increasing from negative infinity to positive infinity. So what does that tell us about 6? 6 is always, do we have any maxes or mins? We have none. All right. Okay, now step 7 is going to be second derivative, going through that whole work again and kind of doing that process again. So kind of like the other problems, I'm gonna kind of get us started, and then I'm going to give you what the end result is, and for you to kind of work through that algebra on your own, just because of time purposes, right? So here's your first derivative, right? X to the fourth plus 3x squared. I like to write it down so you guys have it as a reference. That's our first derivative. So we're going to say u is equal to x to the fourth plus 3x squared. U prime is equal to 4x cubed plus 6x. So a little bit messy. V is equal to x squared plus 1 squared. V prime, so this is a chain rule, right? We have a function inside of a function. So v prime is going to be 2x squared plus 1 to the first power, power rule, times the derivative of the inside, 2x. This becomes 4x times x squared plus 1. Okay. So when I do the quotient rule here, right? So it's going to look a little messy. It's y double prime. So it's going to go v times u prime. So I'm going to call this 4x cubed plus 6x. I'm going to put it in parentheses so I know not to break it apart. Times x squared plus 1 squared minus u times v prime. Okay, so 4x times x squared plus 1 times x to the fourth plus 3x squared all over v squared. So this is going to look like x squared plus 1 to the fourth. All right, so a little bit of algebra here. It simplifies down. Everything has a factor of x squared plus 1, so you can cancel one of those out. And believe it or not, this thing actually simplifies all the way down. We're going to end up getting negative 2x times x squared minus 3 all over x squared plus 1 cubed. Ooh, a little blurry. All right. All the way, some algebra, right? If you want to practice that algebra, I really encourage you guys to do that and get through that. So this is what we get. We set the top equal to 0. We set the bottom equal to 0. We've already talked about it. The bottom never equals 0. And the top, well, the top's going to equal 0 when negative 2x is equal to 0. So at x is equal to 0. And at plus or minus root 3, right? X squared minus 3 is equal to 0. X is equal to plus or minus root 3. So those are our potential points of inflection. So our set up our intervals. We're going to go from negative infinity to negative root 3, negative root 3 to 0, 0 to root 3, and then root 3 to positive infinity. Root 3 is like 1.73 and change, right about there. All right, so that just helps you with your thinking about your test intervals. So like negative 2, negative 1, 1, and 2 would work out. And then sine of the second derivative. Second derivative, this would be negative 2 times negative 2, which would be a positive. This guy would be positive over a positive. This thing is just going to be positive. You can always plug it in to check, right? Negative 2 times negative 1 is going to be positive. Negative 1 squared minus 3 is going to be negative. Positive times a negative, negative, over something that's always going to be positive. So this is going to be negative here. 1 will be positive, and then 2 is going to be negative again. All right, so you can go through that and kind of check that. All right, so what does 7 tell me? 7 tells me that we are concave up from negative infinity to negative root 3 and from 0 to positive root 3. And we are concave down, lost my train of thought here, from negative root 3 to 0 and from root 3 to infinity. We have 3 points of inflection, right? We go from concave up to concave down at negative root 3. We go from concave down to concave up at 0. We go from concave up to concave down at 2. So points of inflection, negative root 3. And when you plug in negative root 3 into the original equation, you're going to get negative 3/4 root 3, all right? Or whatever that decimal equivalent is. Feel free to get that decimal. When I plug in 0, I'm just going to get 0. We've kind of already done that problem. And when I plug in positive root 3, I'm going to get positive 3/4 root 3. All right, so those are all of our points of inflection for this curve, all right? Now, on the next video, I'm going to show you what the graph looks like so that you guys get an idea of what this picture is, and kind of show you what to do. This question shows up in your homework. It doesn't show up on your exam, but why I really still wanted to do this problem, obviously because it's on your homework, but like anytime we can get that derivative practice in, to me, it's always a good thing, all right? So when the next video, I'll show you what this graph looks like so that you can get an idea and we can see what that slant asymptote is.